Okay, and I will start sharing my screen. I think we already reached FM signal. So sorry, where are we? Okay, I think previously we have learned up to this slide, right? If I'm not mistaken, we have learned up to this slide previously. Can somebody confirm me about this? I think we stopped here previously, right?
Yes.
Okay, thank you for the comment. Okay, thank you for the response. So, okay, so we will begin with this topic. Okay, so maybe before that we can do some refresh what we have learned so far. Okay, so okay, so for angle modulation for both FM and PM, remember frequency modulation is the process of changing the frequency of the carrier in accordance with the amplitude variation of the input message signal, whereas the phase modulation is the process of changing the phase of the carrier in accordance with the amplitude variation of the input signal. Okay, and we have learned about this general equation for angle modulation. So this is for both FM and PM. Okay, so it is equal Vt is equal to Vc sine in bracket 2 pi fct plus theta t. So theta t is the function of modulating signal or the input message. Okay, so you're gonna see later that these parameter theta t will change in accordance with the input variation. Okay, and you're gonna see that in some other literature books they use cosine function. Okay, so no problem, don't worry about that, because this is from Wayne Thomas's book. He uses a sine function, okay, for the general angle modulated signal equation. Okay, so my advice to you about the general equation, you should remember about this bracket. Okay, because many students did careless mistakes about this. Okay, so everything here belongs to the sine function, so remember that, because if you do careless mistake here, the rest of the question will be wrong. Okay, because this is the fundamental first question. Normally we ask you about the equations, and the rest of the sub questions we ask you to find some parameters, for example like the power calculation and so on. So this equation must be correct. Okay, remember that. And input message VMT, we have learned about this. Okay, and we have learned that theta t is the instantaneous phase deviation in radians. So instantaneous phase is the instantaneous change or instantaneous variation of the phase at specific time, whereas the instantaneous phase is the exact or precise phase of the carrier at a specific time. Okay, also in radians. Okay, omega ct plus theta. And if you do the first derivative of theta t, you're gonna get theta prime t. Okay, if you do dt of theta t, you're gonna get theta prime t. Okay, and this is what we call, theta prime t is what we call as the instantaneous frequency deviation. It is the instantaneous change or instantaneous variation of the frequency of the carrier at a particular of time. Okay, and the unit is radian per second, or in terms of hertz. Okay, and since we do the first derivative of theta t, so if we want to get theta t again, that means we need to do the integral process of theta prime t, okay, over t. Okay, and then if we do the first derivative of omega ct plus theta t, so we're gonna get omega c plus theta prime t. So this is what we call as the instantaneous frequency, which defined as the specific frequency of the carrier at a specific time. Okay, and we have seen about this a deviation sensitivity parameter, Kp and Kf. Okay, so Kp is the phase deviation sensitivity parameter. Okay, whereas Kf is the frequency deviation sensitivity parameter. So we can rewrite the equation for theta t and theta prime t. So theta t is equal to Kp Vm Kp Vmt, whereas theta prime t is Kf Vmt. Okay, so this is in term theta t in radians, theta prime t in radian per second, or in term of hertz. Okay, and Kp, the phase deviation sensitivity parameter, the unit is radian per volt, or it is actually the difference of theta over the difference of voltage. Whereas for the Kf, which is the frequency deviation sensitivity parameter, the unit is radian per second per volt, or hertz per volt. Okay, so it is defined as the difference of omega over the difference of voltage. Okay, so we have asked this kind of question previously in the exam. As I told you before, that we give the student a table, okay, which shows the reading of, for example, the reading of omega and also voltage. So you're gonna get x1, x2, x3, something like this. So we give you the values. Okay, so in order to find the Kf, so you need to do, for example, x2 minus x1 divide with y2 minus y1. Okay, so the value is actually given in the questions. This is an example of the previous final exam. Okay, and actually you can also do, it is actually any adjacent values. So actually you can do also, for example, x3 minus x2, for example, divide with y3 minus y2. So you can take any two values side by side, so that you can find the Kf, because this is a linear values. Okay, so again, as I mentioned, that theta t can be calculated by doing the integral process of theta prime t. Okay, so we know theta prime t from the previous slide, which is this one, Kf Vmt. So we can put inside the equations, okay, Kf Vmt. So we can do the integral of Vmt. Okay, and then we can rewrite again the complete equation for each of Pm and also the Fm. Okay, so from the general equation, this is the general equation, we can rewrite the general equation for phase modulation, which is Vc sine in bracket omega ct, or you can write 2 pi f ct plus Kp Vm sine omega mt, or sine 2 pi f mt. Okay, omega is 2 pi f. Okay, omega is 2 pi f. Okay, so this is the general equation for phase modulation. Okay, for phase modulation you can use this general equation. Okay, And later you're gonna see that this parameter is actually referring to the modulation index. Okay, you're gonna learn about this later after this. Okay, and for the frequency modulation, we can rewrite the equation based on the general equation of the angle modulation equation. So we can write it as like this. So this is the general equation. So we can replace theta t with integral of theta prime t. So we put the values kf vmt. Okay, integral of kf vmt. So vmt is vm sine omega mt. So vm is a constant value, kf is also a constant value, so you can put outside, and you can do the integral of sine function. Okay, integral of sine, you're going to get negative cos. Okay, negative cos over omega m. Okay, so this omega m is actually 2 pi fm actually. Okay, so remember omega is 2 pi f. Okay, so this is 2 pi fc. Okay, so you get the general equation for frequency modulation. Okay, so if you see from here, we use the sine function. So there's another example which use the cosine function, which is this one. Okay, so in this example, you're going to see that you are given the general equation as cosine, and you are given modulating signal equation as cosine also. Okay, so normally in the exam, either we give you sine and sine, or we give you cos and cos function like this. Okay, so no problem, so don't worry about that. Okay, so we normally give you sine and sine, or cos and cos functions, so that you can define the equation. Okay, so therefore we can rewrite the phase modulation equation as Vc cos. So we change theta t into Kp Vmt. So how does it change to be like this? It is based on this equation, based on this so I flash back. So theta t is Kp Vmt, theta prime t is Kf Vmt. So we can put inside the theta t as Kp Vmt. Okay, so put inside here Kp Vmt, so you get Kp Vm cos omega mt. Okay, because Vmt is equal to Vm cos omega mt. Okay, so again you can change the omega c as 2 pi fc. Okay, 2 pi fct, and here is 2 pi fmt. Okay, so you can write either as omega, or you can write as 2 pi f. Okay, and for the frequency modulation, okay, so we can do the integral from the general equation. So we put inside from the general equation, this is Vc cos. So Vc cos big bracket omega ct plus integral of theta prime t dt. Okay, so theta prime t dt is equal to so from general equation, so from general equation we change theta t into integral of theta prime t. Okay, so integral of theta prime t, okay, so integral of theta prime t is equal to integral of kf vmt. Okay, so integral of kf vmt, it is integral of kf vm cos omega mt. So put upside the constant parameters. So integral of cosine, you're gonna get positive sine over omega m, or 2 pi fm. Okay, so this is actually 2 pi fm. Okay, and here is 2 pi fct. Okay, so I just change omega with 2 pi f, so that you can see from two different perspectives, either using the omega or you want to use the 2 pi f. Okay, and we have seen about this also, about the variation of frequency of the carrier. Okay, remember in angle modulation for both FM and PM, okay, when you change the frequency of the carrier, you are actually indirectly change the phase of the carrier, because the frequency and phase are related to each other. Okay, so kalau kita tukar frekuensi carrier dalam proses modulation, we are actually indirectly change the phase of the carrier as well. Okay, so what about the amplitude? Okay, amplitude of the carrier remains the same. Okay, amplitude of the carrier remains the same. Only the frequency and phase will change. Okay, so if you see from here, what happened actually? Okay, so from this picture, it wants to show you the variation of the frequency in accordance with the variation of the amplitude of the input message. Okay, so you see that here the center here is the rest frequency. Okay, the rest frequency of the rest of carrier frequency, which is Fc, and when the input message amplitude change from 0 until positive peak amplitude, okay, until positive peak amplitude, which is Vm, what happened to the carrier frequency is that carrier will reach the maximum frequency. Okay, and then the input message signal reach the center, reach the 0 crossing. So what happened is that the carrier frequency would be at rest frequency, which is Fc. Then the amplitude of the input message change to the negative peak, which is negative Vm. What happened to the carrier frequency? Okay, the carrier frequency would be at minimum, which is Fc minus delta F. And then the amplitude of the input message change again towards the 0 crossing, or the 0 part here. So the carrier frequency becomes Fc again, rest frequency. Okay, so the difference here, you're going to see that the difference of the carrier frequency is delta F and delta F. So delta F, this is what we call as the frequency deviation parameter, and 2 times delta F is the maximum deviations from positive to negative. Okay, so 2 delta F is what we call as the carrier swing. Okay, carrier swing. Okay, carrier swing. Okay, so carrier swing is also is an important parameter. We also have asked these kind of questions in the final exam. We ask the students to find the carrier swing parameter. Okay, and then again about this picture. Okay, so this picture wants to show you the how does the variation of the waves when the input message change the amplitude. Okay, when the amplitude of the input message change, what happened to the FM and PM signals? Okay, so if you see from here, the above picture here, A is VCT, and then picture B is modulating signal, which is VMT, and then picture C here is VFMT, and picture D here is VPMT for phase modulation. Okay, so you see that FM and PM signals looks similar. Okay, FM and PM signal looks similar. So we need to see so the difference is in terms of what actually. Okay, so in order to find the difference, you need picture A and B so that you can identify the differences. Okay, so you see that carrier at the beginning, so let's see picture a graph C. Let's see a graph C for the FM. Okay, at the beginning, carrier would be at rest frequency, which is the original frequency of the carrier, which is Fc. Okay, then what? The input message signal, modulating signal, move from 0 until positive peak. What happened to the output signal? Okay, the FM signal will have the maximum negative deviation, which is the minimum frequency. So the carrier frequency would be, at this point, it would be Fc minus delta F. Okay, so the carrier frequency would be at minimum at this time. That's why you're gonna see that the wave, the ripple of the wave is is further away from each other. Okay, so it is a minimum frequency. Okay, and then what? The input message signal move towards zero crossing or the x-axis. Okay, so at this point, what happened to the carrier frequency? So the carrier frequency would be at rest frequency. Okay, what is rest frequency? Rest frequency is Fc. Okay, the original frequency. And then what? The input message move towards negative peak amplitude. So the output signal, which is the FM signal, will have the maximum positive deviation. Okay, so what happened here? You see that the ripple is very close to another. So this is actually the maximum frequency of the carrier. So the carrier frequency would be at Fc plus delta F maximum. Okay, and then the input message move towards zero crossing. So the FM signal would be at rest frequency, at carrier rest frequency, which is Fc. Okay, so you see that the difference happen at the critical change happen during the peak amplitude of the input message. Okay, perubahan ketara berlaku pada peak amplitude of the input message. This is for the case of frequency modulation. Okay, and then what? What happened for graph D, which is for phase modulation? So what's the difference? So I will show you. Okay, so I will erase this one because I want to show you for the phase modulation. Okay, graph D. Okay, so phase modulation, you're going to see that the critical change happens when the input message cross the zero crossing, whereas when the input message at peak amplitude, the output gonna be at rest frequency. Dia terbalik. Okay, it will be slightly different. Okay, so you're gonna see that from the beginning. Okay, picture D, graph D. At the beginning, the carrier will be at rest frequency, Fc. Okay, and you're gonna see that the input is actually moving from zero towards positive peak. Okay, so at this point, actually, the frequency is maximum, which is Fc plus delta F. Okay, and then the input message reached the positive peak amplitude. What happened? So at the output, the carrier frequency would be at rest frequency, which is Fc. Okay, and then the input message move from positive peak towards zero crossing. So once it reached zero crossing, so this is the movement from positive towards negative. Okay, and critical change happen. Okay, so the output message, the output signal would be at maximum negative variation. The carrier frequency at this point would be minimum, which is Fc minus delta F. Okay, and then the input message signal move from zero crossing towards until it reached the maximum negative peak. So what happened at the output? The output would be at rest frequency, and at this point carrier would be at frequency Fc. Okay, then the input message move from negative peak towards zero crossing. What happened to the output? The output would be at maximum positive deviation, and at this point carrier frequency would be maximum, which is Fc plus delta F, and so on, dan seterusnya. Okay, so for summary, for phase modulation, critical change happen during zero crossing of the input signal, whereas for the frequency modulation, the critical change happen when the input message reach the peak amplitude, either peak positive or peak negative. So that's the difference. And if you see from both graphs C and D, the amplitude of the carrier remains the same. Okay, amplitude carrier tidak berubah sebenarnya. If you see from here, if you compare graph C and D with graph A, the amplitude of the carrier, okay, the amplitude of the carrier remains the same throughout the process. Okay, remains the same. Okay, the amplitude of the carrier remains the same. Okay, only the frequency and phase are changed. Okay, so previously we have asked about phase modulation actually. This one, picture D, graph D. We have asked in the final exam, where we give, I think we give student 3 graph, carrier, modulating signal, and also the PM signal. And we have asked the student to answer what happened at certain point. Okay, what happened to the frequency of the carrier? Is it maximum or minimum? We have asked that kind of questions before. Okay, pernah ditanya soalan seperti itu. Okay, so you need to understand where are the critical points. Okay, you need to understand about that. Okay, phase deviation and modulation index. Okay, so class, if you have questions, if you don't understand, please ask me question. Okay, you are most welcome to ask question anytime. Okay, if you don't ask question, I will move to the next slide. Okay, ada yang nak masuk ke? Sekejap. Wait. Okay. Okay, phase deviation and modulation index. Okay, so now we want to learn about the modulation index. Okay, so modulation index is defined as beta. Okay, so for PM, the modulation index is defined as beta P. Okay, so the parameter in front of the sine function is what we call as the modulation index. So therefore beta P is actually equal to kpVm. So this is supposed to be capital V, because this is the peak amplitude of the message. Okay, remember here is actually previously, if you remember, that this is supposed to be kpVm. Okay, and this modulation index for the phase modulation has a unit, which is in terms of radians. Okay, it has a unit. Okay, So beta P represent the peak phase deviation in radians for phase modulated carry known as modulation index. So one primary difference between PM and FM is how the beta P is defined. For PM, modulation index is proportional to the amplitude of the modulating signal and independent of its frequency. Of course, you see from here, beta P is proportional to the VM. The higher the VM, the higher would be the modulation index. Okay, so this beta P is not related to the modulating signal frequency FM. Okay, regardless of what frequency you use for the modulating signal, is still the same. Okay, it will change only based on the peak amplitude of the modulating signal, which is VM. Okay, and you're gonna see later what happened to the modulation index for FM. Okay, it's slightly different. Okay, so we're gonna see about that later. Okay, so beta P is equal to Kp Vm. So the unit for Kp is radians per volt. Okay, and if you multiply it with peak amplitude of the modulating signal in terms of volts, so you're gonna get the output. The output value is, okay, the final value is in terms of radians. Okay, so this is beta P. What about for the frequency modulation? Okay, so as I mentioned previously that the parameter in front of okay, the parameter here in front of cos, okay, previously in front of sine. Okay, so the parameter in front of this sine or cos function is defined as modulation index. Okay, so since this is for the FM, so the front parameter here is what we call as beta F. So beta F, if you still remember that the parameter here is actually Kf Vm over omega m, which is, as we have learned from this slide. Okay, either this is or this is this one. So it is actually referring to this. Okay, so this is beta F. Okay, this is beta F. Okay, so beta F is equal to Kf Vm over omega m, or you can write like this: Kf Vm over 2 pi Fm. Okay, and in this case, Kf is equal to radians per second per volt. Okay, and beta F is a unitless parameter, different from beta P. Beta P has a unit which is in term of radians. Okay, beta P ada unitnya adalah radians, whereas beta F is a unitless parameter. So in this case, Kf is defined as radians per second per volt, divide with radian per second. So if you see that volt multiplied with volt, and then radians per second divide over radians per second, so you're gonna get a unitless value. Okay, a unitless value. And if you see in this slide, okay, beta F can also been written as Kf Vm over Fm. Okay, we can also write beta F as Kf Vm over Fm, but in this case, Kf is in term of hertz per volt. Okay, so we need to see the unit for the Kf actually. Okay, so in this case, Kf is equal to hertz per volt. Okay, so hertz per volt multiplied with volt, you get hertz. Hertz divide with hertz, so no unit. It's a unitless parameter. Okay, normally most of the time in exam we use this equation for the beta F. because we're going to give you in the exam, normally in the exam, we give the value of kf in term of hertz per volt. Normally, okay, biasanya kita bagi dalam sebutan hertz per volt. Okay, so both of these are the same. Either you want to use this, but this one is the difference is in term of kf. Kf is radian per second per volt. Okay, whereas for this one, kf in term of hertz per volt. Okay, so slightly different. So the difference is actually we divide actually above and below with 2 pi. Okay, so if you divide above and below with numerator and denominator with 2 pi, so you're gonna get like this. Okay, hertz per volt, like this, divide with hertz. Okay, it is actually the same actually. Dia adalah benda yang sama. Okay. Frequency deviation, delta F. Okay, so delta F or delta FC, okay, delta F or delta FC, same, okay, is equal to kf Vm, or delta theta is the phase deviation, is defined as kp Vm in terms of radians. Okay, so this is important parameter. Okay, important parameter. Okay, so for example, a sample of transmitter with assigned rest frequency 100 megahertz deviated by plus minus 25 kilohertz. So the carrier change frequency with modulation between the limits of 99.975 and 100.025. Okay, so the total frequency change is 25 times 2, what we call as the carrier swing. So what is this actually? Okay, so if you want to understand about this, you need to draw the frequency spectrum. Okay, this is F. So the rest frequency, okay, they said that the rest frequency is the center frequency. Okay, rest frequency is the center frequency, which is, this is in terms of megahertz. Okay, and then what? The carrier frequency deviates. Sorry. So I make this one. I make this one. So the carrier frequency deviates 25 k and also 25 k, that negative side. Okay, another 25 k. Okay, so this is delta F actually, delta F. Okay, so therefore the deviation, since deviation is 25k, that means the maximum frequency is 100.025 mega, and here is 99.975 megahertz. Okay, so therefore the carrier frequency deviates from 99.975 until 100.025, and the rest frequency is 100 megahertz. Okay, so this 25 kilohertz is actually what we call as the frequency deviation, delta F. So 2 times delta F, okay, 2 times delta F is what we call as carrier swing. Okay, remember in angle modulation, the carrier frequency change in accordance with the input signal variation. Okay. Okay, so it mentioned about table 1, so we're gonna see about table 1 later about this. Okay, next slide. So since delta F is equal to kf Vm, okay, since delta F is equal to kf Vm, so we can rewrite again the equation. Okay, we can rewrite the beta equation as delta f over fm. Okay, remember this is actually kf Vm over Fm. So this Kf Vm is delta F. Okay, and if you rewrite the Fm equation, it becomes like this. Okay, you just need to change this one, which is, this is also the beta parameter, beta F. Okay, so this omega Ct is actually 2 pi F Ct. Okay, this is 2 pi F M. Okay, so I just change omega with 2 pi F. Okay, so FM signal. So now we want to focus on the FM. So FM signal can be divided into two categories, narrowband FM and also wideband FM. So narrowband means small bandwidth, wideband means bigger bandwidth. Okay, big bandwidth. Okay, so the narrowband and wideband is actually referring to the bandwidth of the signal, the bandwidth requirement. Okay, how big is the bandwidth required by this signal? Okay, so narrowband means small bandwidth, wideband means bigger bandwidth, big bandwidth. Okay, so narrowband and wideband, we can classify narrowband and wideband FM based on the value of beta F. So beta F determines the bandwidth of the signal. Okay, it determines the bandwidth requirements. So the higher the value of beta F, okay, the higher the value of beta F, the wider would be the bandwidth. Okay, so if beta F is higher, we need higher bandwidth. So this is wideband FM. Okay, so if beta F is small, so the bandwidth requirement would be small. So this is under the category of narrowband. So how big is big, how small is small actually? So we're gonna see about that later, okay, in the next slides. Okay, so before we learn about narrowband and wideband, so we need to look from this perspective. Okay, so this is table 1. Okay, what important here is actually the first row. Okay, the first row is important. Sorry, the first row here is important about the frequency modulation, broadcast frequencies. So it is between 88 until 108 megahertz. So this is the total FM band. Okay, this is defined by the standard. Okay, if you see from your radio, it is between 88 until 108 only. And within this bandwidth, we're gonna have many radio stations. Okay, we can have many channels or many radio stations. Okay, so channel or radio station, each of it has a bandwidth of 200 kilohertz maximum. Okay, you can have less but no more than 200. 200 is the maximum. Okay, and maximum deviation or maximum delta F by the standard is plus minus 75 kilohertz. And the highest audio, which is modulating signal frequency, is 15 kilohertz. Okay, and the rest you can read on your own for television, public safety applications, amateur radio, wireless mics and wireless telephones, video tape recorders, satellite and military applications. They use a different kind of frequency assignment. Okay, so you need to you can read on your own, but the first row is important. Okay, so in the previous exam, normally in the exam we ask question from here between 88 until 108 megahertz. How many radio station we can allocate within this specific bandwidth? Okay, so you're gonna see later in the next slides there is example about this. Okay, I'm gonna explain to you later how many radio station we can put inside this FM band. Okay, so the next topic is percent modulation. Percent modulation is the ratio of actual delta F divided with maximum delta F defined by the standard or defined by the law. So since this is percent, so actually you need to multiply it with 100%. Okay, we need to multiply it with 100%. For example, okay, this is the example. Given the modulating signal produce plus minus frequency deviation, so this is actually delta F actual. Okay, and the law stated that the maximum frequency deviation allowed is 75 kilohertz. So this is delta F max. Okay, then the modulation, the percent modulation is equal to delta F max, sorry, delta F actual divide with delta F max defined by the standard and multiplied with 100%, so you're gonna get around 67%. Okay, so if you see from here, 50 divided 75, so you're gonna get 66.6666. Yeah, so in the exam, don't round it up the value like this. So this is just for the example, but in the exam you should write a proper value. It is supposed to be around 66.67%, so more accurate. Okay, okay, if you don't understand, please ask question, otherwise I will move to the next slide. Okay, saya akan teruskan kepada slide example 3.2. Okay, so you can switch on your calculator so that we can answer this question together. Okay, so based on this example, 1 megahertz carrier frequency with a measured sensitivity of 3 kilohertz per volt is modulated with 2 volt 4 kilohertz sinusoid. Okay, so if you see from this example, you are given carrier signal. So the carrier signal has a frequency of 1 mega. Okay, what is this actually? So this is the carrier frequency, which is FC. Okay, and this carrier has a measured sensitivity of 3 kilohertz per volt. What is this actually? So this is actually referring to the KF. Okay, the frequency deviation sensitivity parameter. Okay, and then this carrier is modulated with another signal, which is the sinusoid signal, a sine function signal, and this sinusoid signal has a peak amplitude of 2 volt. What is this actually? So this is actually VM, and the sinusoid frequency is 4 kilohertz. What is this? This is FM, modulating signal frequency. Okay, FM. Okay, so determine what? Determine the maximum frequency deviation of the carrier. So determine frequency deviation. So the question asks you to find delta F. Okay, so delta F, as we have learned previously, it is equal to KF VM. Okay, which is 3 kilohertz multiplied with VM here is 2 volt. Okay, so you're gonna get here 6 kilohertz. Okay, 6 kilohertz. And then what? Question 2. Find the modulation index. So in this example, the question asks you to find the beta f. So beta f is actually equal to kf Vm over Fm. Okay, kf Vm over Fm, or you can write it as delta f over Fm. Okay. So this is supposed to be 6 kilohertz. Divide with 4 kilohertz. Okay, so you get this 1.5. Okay, 1.5. 6 kilohertz over 4 kilohertz. So you're gonna get this as 1.5 kilohertz. Okay, sorry, 1.5, no unit. Okay, 1.5 only, no unit. Okay, so beta f has no unit. Okay, and then what? Question 3. So question 3 asks you find the modulation index if the modulation voltage is double. Modulation voltage is referring to the Vm. Okay, so now the question asks you what is the value of beta f if the value of Vm is double. Apakah nilai beta f sekiranya Vm digandakan sebanyak 2 kali? Okay, so what happened? So now Vm would be so you need to know what is the new Vm. Vm new is equal to 2 volt times 2 because we double it. Okay, so it becomes 4 volt. Okay, and then what? So therefore beta, okay, so beta f, so beta f is equal to kf Vm over Fm. Okay, so kf is still the same, 3 kilohertz per volt according to the question, multiplied with Vm new. Okay, this is Vm new. Okay, Vm new, which is 4 volt, divide with 4 kilohertz. Divide with 4 kilohertz. Okay, so you're gonna get this equal to 3. Okay, so that means if you double the modulation voltage or the input message voltage, what happened is that the beta f would be increased as well. It will be double. Okay, so we have seen the relationship between Vm and also the beta f. Okay, if Vm is double, beta f also will be double. Okay, then question number 4. Okay, so if you don't understand, please ask question, otherwise I will move to the question number 4. Okay, kalau tak faham boleh tanya. So question number 4, determine the modulation index for VMT. So now you are given the modulating signal, the input message, which is equal to 2. So this is a VMT. So Vm cos 2 pi FMT. Okay, so now Vm is equal to 2. Modulating signal frequency Fm is equal to 8 kilohertz. So now the frequency is double. What happened? Okay, what happened? Okay, so I will do here. So the question asks you to find beta f. So the question asks to find beta f. So now you see that Vm still equal to 2 volt. Okay, I do above here. Okay, and then Fm is double as 8 kilohertz. Okay, So now the question asks you to find beta f is equal to kf Vm over Fm. Okay, so kf is 3 kilohertz per volt times 2 volt divide with 8 kilohertz. Okay, so how much is this? Okay, so 6 divide with 8, so you're gonna get 0.75. Okay, which is half of 1.5. Okay, which is half from question number 2. Okay, question number 2 we get 1.5. So since we increase the modulating signal frequency, so the beta f becomes smaller. Okay, half of it. Okay, half of 1.5, which we already got from question number 2. Okay, so now the issue is we increase the modulating signal frequency, so the beta f would be half of it. Okay, separuh daripada 1.5. Okay, which is 0.75. Okay, and then what? Then question number 5, express the FM signal, find the VFMT mathematically for a cosine carrier and cosine modulating signal. So now the question says that the general equation is cosine, the VMT is also cosine. So the VMT is based on part 4, question number 4, which is 2 cos 2 pi 8 kilohertz. Okay, given the carrier amplitude Vc is 2 volt, 10 volt. Okay, so therefore you can rewrite the equation as this one. So VFMT is equal to Vc cos big bracket 2 pi fct plus beta f, or you can write kf Vm. Okay, so kf Vm over Fm, which is a beta f. Okay, sine, if we integral of course you're gonna get positive sine. Okay, so you're gonna be positive sine sine 2 pi fmt. Okay, so kf Vm, we already got this from question number 4. Okay, we already got this from question number 4. Okay, so we can just put inside the equation, it becomes like this. Okay, Vc is given as 10. Okay, given in the question, cos in bracket 2 pi fct, 2 pi fc is 1 mega. Okay, plus kf Vm over Fm, we already find this from question number 4 previously. Okay, which is 0.75. We already got this from question number 4. Okay, 0.75. Okay, kf Vm over Fm is 3k multiplied with 2 divided with 8. Okay, because we are using VMT from part 4. Okay, we are using VMT from part 4, so we're gonna get beta f 0.75. Okay, sine 2 pi, the frequency is 8 kilohertz, 2 pi fmt, so this is Fm is 8 kilohertz. Okay, 8 kilohertz T, so and then close big bracket. Okay, so this is 2 pi FMT, so 2 pi times 10 power 2 pi times 8 kilohertz. Okay, so this is the answer. Okay, for number 5. So if you don't understand this, please ask question. Okay, you can ask question about this. I can further explain if you don't understand. If you understand, that's good. Okay. Okay. So if there's no questions, so I will move to the next slide. Okay, saya akan teruskan kepada slide yang berikutnya kalau tak ada soalan. And this is the summary table for the equations. So in my opinion, you don't need to memorize all of this. You don't need to memorize all of this. Why? Because your final exam is online exam, so you can always refer to the equation in the notes, so no problem. So you don't need to memorize. Okay. Previously, before the COVID pandemic, we give many equations during the final exam. Okay, if you see from the question banks before the pandemic, we include about 2 or 3 pages of equations at the end of the question, so that you can just use the equation to answer the question. Okay, so we actually help the student to answer the question by giving most of the main equations, okay, inside the final exam question. Okay, we give it as attachment to the question. Okay, so this is the summary that we have learned so far about FM and PM. Okay, so you can have a look later about this. Okay, so that you can have better understanding. Okay. So this is the one that I told you how to calculate the total radio station, or how many radio station can be accommodated within the FM band. Okay. So if you see, so for your information, this is the favorite question given in the final exam. Okay, so we have asked this question many times in the final exam. A very simple question. Okay, so if you see from here, this is it shows here that the commercial FM radio band is between 88 until 108 megahertz. So this is the total FM band. So if you can see from your radio, okay, kalau kamu boleh lihat radio kamu, okay, you either in your car or at home, if you have a radio, you can see that FM radio is FM frequency is between this frequency band. Okay, so it is said that each station or each channel, okay, each station or each channel is allotted to a frequency deviation of 75k, okay, plus and minus. So 75 times 2, because above and below, so we get 100 kilohertz. So this is supposed to be 100 kilohertz of carrier swing, and another 25k for the guard band above and below of the carrier swing. So the total bandwidth for one channel or one radio station is 200 kilohertz. Okay, so how does it looks like? So maybe I will draw for you. Saya akan lukis ini, so that you can understand about this. So let's draw the frequency spectrum so that you know what happened actually. So this is F in terms of megahertz, for example. And let's say that the FM band is 88 until 108 here. Okay, so we have a very big bandwidth over here, which is shared by the many radio station, okay, shared by the many radio station. Okay, and if you see the total here, 108 minus 88, you're gonna get around 20 20 megahertz total bandwidth. Okay, total bandwidth. Okay, so let's say I want to listen to radio station what 96 is what 96 is Surya or Sinar FM, something like that. Okay, let's say it's I want to listen to Sinar FM, so if I'm not mistaken is 96 megahertz. Okay, so the center, if I tune to 96 megahertz, that means the center frequency would be 96. Okay, kalau saya tune 96 megahertz, maknanya center frequency berada pada 96. Okay, and given that these channel or these radio stations has a maximum frequency deviation as plus minus 75. Okay, 75k, 75k. Okay, so let's say around here. Okay, so the carrier swing is 75 multiplied 75 plus 75. So the carrier swing is 150 kilohertz. Okay, it is 75 plus 75. Okay, so 150 kilohertz. And it is said that there's another guard band which is 25k. Okay, guard band. So over here is 150. Okay, so what is guard band? Guard band is actually an empty space. Okay, it's like a empty space to avoid the interference from adjacent channel. Guard band ni sebagai ruang kosong untuk menghalang berlakunya adjacent channel interference. Okay, so the signal should not operate at this guard band in order to avoid the interference from the next channel or adjacent channel. Okay, so you see that from here we have another 25 and 25. So therefore, okay, the total here is actually 200k. Okay, 200 kilohertz. Okay, 200 kilohertz. Okay, so if I want to plus 75 and 25, so 75k, so let's try 75k plus 25k, so we're gonna get 100,000. So this is 90, supposed to be 96.1. Okay, because this is 100 kilohertz, 100 kilo, this is 95, so this is 95.9 kilohertz, 95.9 megahertz. Okay, so 96 minus, okay, so 95.9 megahertz. Okay, so between this range of frequency 95.9, okay, 95.9 until 96.1, this is belong to this radio station Sinar FM. Okay, so there's supposed to be no other radio station between these frequencies. Okay, and you know how does the radio station get their own frequency. Okay, so they need to pay to the MC, to the regulators. Okay, they need to bid the frequency. So the frequency band, this is the money to the government, to the country. So if a radio station, if you want to set up a radio station, you want a specific frequency, you need to bid the frequency. So the highest bidder would get the frequency. Okay. Okay. So so that means the total bandwidth for each station is 200 kilohertz. Now we want to know how many radio stations we can allocate in all of this FM band. Okay, so therefore, if you see from here, number of station, we'll do the red color. Number of station is equal to 108 megahertz minus 88 megahertz. This is the total FM band divided with the bandwidth of one channel or one radio station, which is 200K. So you're gonna get 100 station. So we can put 100 station in this FM band at a specific area. Okay. So, for example, in Batu Pahat, within this Parit Raja Batu Pahat, we can allocate 100 radio station at this area. Okay. And if you know that if you move to another area, another cities, the frequency of the radio station will be different. Okay. So that means the frequency, the assigned frequency is actually based on a specific area. For example, in a city in Batu Pahat, so we can set 100 station. Okay. And then maybe in Kuala Lumpur, they're gonna be different radio station. Okay. So at one place we can accommodate up to 100 radio stations. Okay. And for your information, this is the favorite question. We have asked this many times. So this is like a bonus question, okay? So now we're gonna see narrowband and wideband. So first we're gonna learn about the narrowband FM. Narrowband means small bandwidth. How small is it? Okay, normally it is ranging from 10 to 30 kilohertz. Normally. Okay, so modulation index is keep near unity so that the FM band can be determined in a similar manner as AM system, which is 2 times FM. Okay, so you're gonna see later that the bandwidth is actually equal to 2 times FM, which is similar to the AM double sideband full carrier that we have learned previously. Okay, remember in double sideband full carrier, the bandwidth is 2 FM, and it is considered as big for AM. Okay, but in FM, this bandwidth is considered as small. Okay, so FM frequency modulation needs actually wider bandwidth compared to the AM. Okay, sistem FM ini memerlukan bandwidth, sebenarnya memerlukan bandwidth yang lagi besar daripada AM. Okay, so this narrowband system is widely used for the mobile radio system for the police, fire and taxi services, cellular telephony, amateur radio and so on. So there are many applications that use the narrowband FM. Okay, so let's look into the equations. Okay, so assume that the carrier signal is Vc cos omega Ct, and modulating signal is equal to Vm cos omega Mt. Okay, so the resulting VFMT is equal to Vc cos omega Ct plus beta f sine omega Mt. So in wideband FM, the beta value, the modulation index is small. Normally, most of the time is less than 0.25. Okay, so if less than 25, if the beta parameter is small, we can do approximation for a certain parameters. Okay, and if you see that from the FM equations, this is actually cos A plus B. There are two parts here, omega Ct and beta f omega Mt. So this is like a Vc cos A plus B. Okay, and according to trigonometry identity, we can elaborate this equation. Okay, so I'm going to show you about this approximation later. Okay, what happened to this actually? So from the general equation of Fm, we can elaborate the equation to become like this. Okay, so according to trigonometry identity, cos A plus B is actually equal to cos A cos B minus sin A sin B. Okay, so we can put inside the equations. Okay, cos A is Vc cos omega Ct. Cos B, what is cos B? Cos B is this one. Okay, so cos of B is approximately equal to 1 if beta f is small. Okay, this is the approximation that they have made. Okay, so therefore this is actually multiplied with 1. Okay, minus sin A, Vc sine omega Ct, sin B. What is sin B? Sin B is sine of B is sine beta f sine omega Mt, which is approximately beta f sine omega Mt. So this approximation can be done if beta is very small. Okay, so we can put inside the equation sin B is beta f sine omega Mt. Again, we see that this part is sine and sine. We can further elaborate this part. Okay, sine and sine, according to trigonometry identity, it becomes cos A minus B minus cos A plus B. So this is what we have done in the AM. Okay, so cos A minus B minus cos A plus B. Okay, so we get a lower sideband and upper sideband. Okay, so what happened? Vc cos omega Ct plus, so you see that it becomes plus here. So that means this A plus B will be in front. So 1 over 2 beta f Vc cos 2 pi upper sideband. Okay, so since minus, you see that minus and minus, so we get plus over here. Okay, minus and minus will become plus, so it put plus over here. So for the upper sideband, so 1 over 2 beta f Vc cos 2 pi Fc plus Fmt minus the lower sideband. Okay, so if you see from this equation, we have three components: the carrier, the upper sideband, and also the lower sideband. Okay, and this is similar with the double sideband full carrier that we have learned in AM. And if you draw the spectrum, what happens is that you're gonna get three components like this. Okay, center at Fc with the amplitude of Vc, and the upper sideband is located at Fc plus Fm with the amplitude of 1 over 2 beta f Vc. and the lower sideband located at Fc minus Fm with the amplitude of 1 over 2 beta F Vc. Okay, and the bandwidth is Fm and Fm, so the bandwidth is 2 Fm. Okay, and if you want to find the total power, so the total power you need to plus all of this. Okay, so total power is equal to PC plus PUSB plus PLSB. Okay, LSB. Again, this is BC square over 2R plus 1 over 2 beta F BC square over 2R plus 1 over 2. Okay, so you can get the total power. So this is for the narrow band. Okay, so the narrow band, the bandwidth is 2 Fm. Okay, so what about the wide band? Wide band FM. So wide band FM means that the bandwidth is bigger or wider. Okay, so from the general equation, we see that Vc cos 2 pi Fct plus beta sine 2 pi Fmt. So this beta parameter will determine the bandwidth of the FM signal. Okay, so there are two methods to determine the bandwidth. The first method is to use the Bessel function. Another method to determine the bandwidth is to use the Carson's rule. You will see later about this. So now we want to see about the relationship of the beta and also the bandwidth. So what is the relationship? So you're going to learn about this. This one. This is very important. Okay. Wait, so since this is important, so I need to drink first. Okay, so this is what we call as a Bessel function table, which define the relationship between the beta parameter and also the sideband parameter. Okay, so if you see from the first column here on the left, it is a modulation index beta F from 0 until 8. Okay, and then we have the next column is carrier component J0. Okay, and then the sideband component from J1 until J10. Okay, so these sidebands are the pair of sidebands. We have the upper and also the lower. Okay, it shows the number of how many pairs of sidebands. Okay, and the value of the carrier and sideband component is related to the relative amplitude. Okay, so all the values that you see from J0 until J10 is actually what we call as the relative amplitude. Okay, so what is the relative amplitude? It is Jn equal to Vn, the real amplitude, divided with carrier amplitude. So it is a unitless parameter actually. Okay, and if you want to find the real amplitude, that means Vn is equal to Jn multiplied with okay, So if you want to find the real amplitude Vn, it is Jn multiplied with Vc. Okay, and if you see from this table, there is negative values. So the negative values is actually showing about phase shift. Okay, 180-degree phase shift in the carrier. Okay, berlakunya perubahan fasa sebanyak 180 darjah pada carrier. So that's why the polarity change to negative. It's not because the value is small, no. It is because happens the carrier change happens inside for about 180 degree. And this has been explained in the next slides about this one. It's already stated here that the negative is actually to show the phase shift for about 180 degree. Okay, 180 degree phase inversion. Okay, what else? So if you see that the higher the value of beta, the more would be the sideband, the number of sideband. Okay, for example, here, if beta is 1.0, okay, I gonna have up to 3 pairs of sideband. Okay, and another example, if beta is 8, equal to 8, I gonna have up to 10 pairs of sideband. Okay, so kalau saya ada beta sama dengan 8, saya akan ada 10 pasang sideband. Okay, another example, if the beta is 2.0, I gonna have up to 4 pairs of sideband. So the larger the value of beta, the more would be the sidebands. Okay, lagi besar nilai beta, lagi banyak sidebandnya. Okay, so that means if there's more sideband, that means the bandwidth will be wider. Bandwidth menjadi semakin besar. Okay, so we're gonna see about this after this. So and then this picture wants to show you the relationship. For example, this is up to 6. So this is up to 6 pairs of sideband. Okay, up to 6 pair of sideband. So if I look from here, 6 pairs of sideband, it is actually referring to this one actually. Okay, beta equal to 3, it is up to 6 pairs of sideband. Okay, and the way we want to draw the spectrum, how can we see the spectrum? Okay, how can we see the spectrum? So the spectrum looks like this. For example, beta is equal to 3.0, and according to the table, it is up to 6 pairs of sideband, sehingga 6 pasang sideband. Okay, so how can we draw the spectrum? So if you draw the spectrum, center at Fc, and then the next is Fc plus Fm, Fc minus Fm, and then Fc plus 2Fm, Fc minus 2Fm, Fc plus 3Fm, Fc minus 3Fm, and so on until Fc minus 6Fm and also Fc plus 6Fm. Yes? I have class later. Yeah. Okay. So the total bandwidth, the total range of sideband is from Fc minus Fm until Fc plus 6Fm. Okay. So again, this is the location of the frequencies. So the amplitude. So the amplitude is, this is J0, okay, and then this is J1, this is J2, this is J3, J4, okay, J5, J6, J6, okay. So we get up to 6 pairs of sidebands, okay. So we have upper and lower sidebands, okay. And sorry, this one, the Bessel table in your notes has omit or neglect the value less than 0.01, okay. So table dalam nota itu, dalam nota kamu ini, this table has omit the values of sideband less than 0.01, okay. So they might be actually more, maybe, okay, they might be more than the specified bandwidth, the specified number of sideband, because this table in your notes has neglect or omit the sideband value less than 0.01 because it is very small, okay. So if you search in the Google, okay, Bessel function table, it will show you the all the details, okay, of the sideband values up to very small values of sideband, okay. So if you ask me, this table is not very accurate, okay, it's not 100% accurate because it has omit the value less than 0.01, but no problem, okay, we can still use it. Even in the exam we will give you this table, so you can give your answer based on this table, okay. And the Bessel table is actually produced based on this Bessel function, okay. Sebenarnya table tadi diperoleh berdasarkan graph ini, okay. We produce the table based on this graph actually, okay. So this is a J versus beta, okay, J versus beta functions, okay. So if you have a ruler, okay, if you have a ruler, okay, you can try on your own, you can try on your own. For example, beta equal to 1, for example, beta equal to 1, you can use your ruler, okay, use your ruler, and then you can see where the line will cross, okay. The line will cross at J3 and then J2 and then J1 and then J0, okay. So you're gonna have up to J3, okay, from J0, J1, J2 and J3 for beta equal to 1, and you can try the rest, okay. So for simplicity you can use the table, okay. So you can read on your own about this. So we move to this slide. So how to determine the transmission bandwidth of FM signal? As I mentioned previously, that we can determine the bandwidth for the wideband FM using two methods. Either we want to use the Bessel function or we want to use the Carson's method, okay. So if you want to calculate the bandwidth using Bessel function, we can use this equation, bandwidth equal to 2 times n times Fm hertz, okay. N is the number of significant sideband, n is the number of pair of sideband, how many pair of sideband, okay. For example, if I flashback, for beta equal to 1, okay, for beta equal to 1, you're gonna see that it is up to 3 pairs of sideband, okay, up to 3 pairs of sideband. So therefore n, okay, n is equal to 3. There are 3 pairs of sideband for modulation index equal to 1, Okay, so this is example. Okay, okay, so if you want to know the more about this, then we can do the example like this, example 3.3. okay, so example 3.3, calculate, okay, before that bandwidth by Bessel. Normally we write like this, bandwidth by Bessel. Okay, BW subscript Bessel. So bandwidth by Bessel is known as the actual bandwidth. Bandwidth Bessel ini juga dikenali sebagai actual bandwidth, bandwidth sebenar, bandwidth yang tepat. Okay. So calculate the bandwidth occupied by FM signal with a modulation index of 2. Okay, so bandwidth beta is equal to 2. Okay, beta is equal to 2, and the highest modulating frequency is 2.5K, which is, this is a modulating signal frequency FM. Determine the bandwidth table, the bandwidth with table of Bessel function. So for beta equal to 2, we need to see the from the table how much is the value of n. Okay, so let's look inside the table. Okay, so for beta, so I erase this one. So beta equal to 2, okay, we're gonna have up to 4 pairs of sideband. That means n equal to 4. Okay, so we can put inside the equations. Okay, n equal to 4, so therefore the bandwidth is 2 times n times fm. Okay, 2 times 4 times 2.5, so we get 20 kilohertz. So this is supposed to be kilohertz, this one 2.5 kilohertz. So we get 20 kilohertz bandwidth. Okay, very simple. Then what? Another method to find the bandwidth is bandwidth by Carson's. Okay, bandwidth by Carson. Carson is a person's name. Okay, adalah nama orang. Is a mathematician, where he derived the approximate bandwidth. So bandwidth Carson is known as approximate bandwidth. Okay, so we write it like this: Carson is equal to this one, 2 times delta F plus Fm. Okay, so bandwidth by Carson, you don't need to use table, you don't need to use Bessel table to find the bandwidth. Okay, you can just use your calculator. Okay, so 2 times delta F plus Fm, and you're gonna see later that bandwidth Carson is actually less than bandwidth by Bessel. Okay, bandwidth by Carson ini sebenarnya lebih kecil daripada bandwidth by Bessel. Why? Because this bandwidth is approximation bandwidth. Okay, so you see that there are two people wants to find out about the bandwidth. The one is Bessel. Bessel is another person. Carson is another person. So both come up with a different kind of equations to find the bandwidth. Okay. Okay, let's do example for the Carson's bandwidth. Okay, so assuming that a maximum frequency deviation is 5K, so this is delta F, and maximum modulating signal frequency 2.5K, so this is M. the bandwidth would be, so this is bandwidth by Carson. Okay, bandwidth by Carson is equal to 2 times Fm plus delta F. Okay, so we're gonna get 2 times 7.5k, so we get 15 kilohertz. Okay, 15 kilohertz. So 15 kilohertz. So let's compare with the Bessel. Okay, and if we want to compare with the Bessel, that means we need to find the beta parameter. So actually the beta F is actually equal to delta F over Fm, which is 5k divide with 2.5 2.5k so if beta is equal to 2, this is similar with the previous example. Okay, this is similar with the previous example where we get the value of n equal to 4. Okay, in the previous example, for beta f equal to 2, we get n equal to 4. And the Fm is equal to 2.5. We get the bandwidth by Bessel from the previous example is equal to 30. If you remember this one, okay, so this is actually Fm, so 2 times n times Fm, we get 20. Okay, so 20, sorry, this is 20 kilohertz. So you see that if we use Carson's bandwidth, okay, use the Carson's bandwidth, so this is bandwidth Carson, we get 15 kilohertz. But if you use a bandwidth Bessel, we're gonna get 20 kilohertz. Okay, so by comparing the bandwidth in the preceding example, you can see the Carson rule give smaller bandwidth. Okay, because this is a approximated bandwidth. Okay, compared to Bessel bandwidth is more accurate. Okay, lebih tepat. Okay, so let's do the example. Mari buat example. Okay. Okay. Before that, can I get your response, students? Are you still there?
Yes, sir.
Okay, thank you for the response. Sometimes I'm afraid that I'm talking to myself. Okay, so if you are still there, that's good. Okay, so this example, if you see from this example, for an FM modulator with a modulation index beta f equal to 1, okay, a modulating signal VMT is equal to Vm sine 2 pi 1000 t, and unmodulated carrier is VCT 10 sine 2 pi 500 kt. Determine. Okay, so first you are given beta f. Okay, then you are given VMT and VCT. So Vm we don't know how much, but we know how much is Fm, which is 1 kilohertz. And then we know Vc 10 volt, and we know Fc 500k. So Fm is 1k, Fc is 500k. Okay, so we can determine the rest of the parameters. Okay, determine number of sets of significant sideband. So the question asks about n. How much is n? Number of significant sideband. So for beta equal to 1, okay, for beta equal to 1, if you see from the table, okay, beta equal to 1, you're gonna get up to 3 pairs of sideband. That means n equal to 3. Okay, untuk beta sama dengan 1, maka akan ada 3 pasang sideband. Oleh itu, number of significant sideband is equal to 3. Okay, so therefore this is straightforward, n equal to 3. Okay, and the next question asks you to determine their amplitude. Okay, so again, when you read from the table, you can I flashback to the table. From this table, you can take all the values, J0, J1, J2, and J3. J0 is 0.77, J1 is 0.44, J2 0.11, J3 is 0.02. Okay, so therefore, okay, first of all, I will take note all the values, given values. J0 0.77, J1 is 0.44, J2 is equal to 0.11, J3 is equal to 0.02. Okay, so what is the amplitude? So the amplitude is actually like this. The amplitude is, because remember that Jn is equal to Vn over Vc. So if you want to find the real amplitude, that means Vn equal to Jn multiplied with Vc. Then you can get the real amplitude. Okay, so since the next question asks you to draw the frequency spectrum, so why not I also try to find the frequencies as well? Okay, I can relate with the question number 3, because the next question asks you to draw. So therefore, it is better to have a table. Okay, it is better to have a table, so that not only I can find the amplitude, I can also find the frequency as well. Okay, for example, here is Jn. For example, here is the amplitude in volt, and then we can find the lower sideband frequency. Okay, lower sideband frequency in term of, for example, since we use kilohertz, so we can use kilohertz here, and then here upper sideband in term of kilohertz as well. Okay, in term of kilohertz as well. So this one. Okay, so the amplitude Vn, so that means V0 is equal to 0.77 multiplied with Vc. Vc is equal to 10 according to the question, multiplied with 10, so we're gonna get 7.7 volt. Okay, and this is the center frequency, or the carrier frequency. So there's no lower or upper, because this is at the center. This is located at Fc, which is 500K. Okay, it is located at the 500 kilohertz. And then what? The sideband. The sideband is, the first sideband is 0.44. That means the amplitude is V1 equal to 0.44 multiplied with 10. So we're gonna get 4.4 volt. Okay, and the lower sideband is Fc. Remember that the J0 is located at Fc, so the sideband is, okay, sideband is minus and plus. Okay, so so for the lower sideband, Fc minus Fm, which is equal to 500K minus 1, so we get 499 kilohertz. Okay, and the upper sideband here is Fc plus Fm, which is equal to 500 plus 1, so we get 501 kilohertz. Okay, for the second sideband, the voltage V2, the amplitude is equal to 0.11 multiplied with 10, so we're going to get here is 1.1 volt. So this the second sideband is located at Fc minus 2Fm, which is equal to 500 minus 2 kilohertz, which is 498. And for the upper sideband, Fc plus 2Fm, which is equal to 500 plus 2. Okay, 500K plus 2 kilohertz, so it is actually 502 kilohertz. Okay, then the third sideband, the amplitude is equal to 0.02 multiplied with 10, so we get here 0.2. Okay, so the third sideband is located at Fc minus 3Fm, which is 500K minus 3K, so we get 498 kilohertz. Sorry, 497 kilohertz. Sorry, yeah. 497 kilohertz. While for the upper sideband, Fc plus 3Fm, which is 500 kilohertz plus 3 kilohertz, so the frequency is 503 kilohertz. Okay, so to answer question number 2, okay, we already find all the amplitudes, which is 7.7, 4.4 volt, 1.1 volt, and also 0.2 volt. Okay, based on this equation, Vn equal to Jn multiplied with Vc. Okay, so the next question, since I already make the table, so easy for me to draw the spectrum, frequency spectrum. Okay, question number 3. Okay, draw the frequency spectrum showing their relative amplitudes. So let's draw. So since we have limited space over here, so I will draw above here. So okay, so we will draw here. So when you want to draw, remember, don't use ruler, wasting a lot of time. Okay, so again, when you want to draw the okay, so draw the axis. Okay, draw the axis. So this is okay, so now this is F in terms of kilohertz. Okay, wait, sorry, okay, wait, I want to erase, wait, so this is, so let me draw again. Okay, so this, okay, so frequency F kilohertz. Okay, so the y-axis, we need to see what we want to do actually. Do we have to draw with relative amplitude or power actually? Okay, so the question said that, okay, the question specifically mentioned that you need to relate with the relative amplitude. Okay, which is the J. Okay, the J parameter. Okay, J parameter. Okay, Jn. Okay, so therefore we can draw the spectrum. So this is, for example, the center at 500, okay, which is 0.77, 0.77, okay. And then the first sideband, upper and lower, okay, this is located at 501 and 499, and the relative amplitude is 0.44, okay. And then the second sideband is located at 502, okay, and here is, okay, 498, okay. The relative amplitude is 0.11, and another one here is 0.11. And the third sideband, okay, the third sideband is located at 503, okay, this is 497 kilohertz, and the relative amplitude is 0.02, 0.02. Okay, 0.02. So this is Jn versus F, okay. And remember, if let's say that the question say that draw the amplitude spectrum, okay, let's say the question say that draw the amplitude spectrum, there's no relative over here, tidak ada perkataan relative. For example, contoh so what to do? Okay, that means if the question say that draw the amplitude spectrum, that means you need to draw Vn versus F, okay. So therefore, if it is an amplitude, that means you need to plot the amplitude. So that means this is 7.7, this is 4.4, okay, this is 1.1, this is 1.1, this is 0.2, and another one 0.2, okay. And another one is that there's also a possibility that the question asks you to draw the power spectrum. Boleh juga, okay, power spectrum. So what to do? Okay, so if it is a power, that means you need to find the power Pn. Sorry. Let me erase this one. So power equation is still the same, okay, power. So power Pn is equal to Vn square divide with 2R. Okay, so you need to find the power. So it needs to know, you need to know the resistance value. Okay, so if it is a power spectrum, for example, so you need to draw Pn versus F. Okay, that means over here is P0, over here is P1, over here is P1, and then P2, and then here P2, over here is P3, P3. Okay, so this is the power spectrum. So it depends on the question. So what the question wants actually, relative amplitude spectrum, or power spectrum. Okay, so do you have question about this? If not, we can look to the next example. Okay, kalau tak ada soalan, kita boleh lihat example seterusnya. Okay, if you have question, please ask. I can further explain to you. If not, then we can look the next example so that you can have better understanding. Okay, so no question. Hopefully you understand this. So I will move to the next example, this one. Okay, example 3.5. 3.5. So how to do this? So let's try. Okay, so I suggest you to have a calculator and a piece of paper to write the answer. Okay, to write the answer. Okay, so don't copy the question. Okay. Okay, again I want to remind you, in the test or in the exam, please don't waste your time to rewrite the question in the answer book. Okay, jangan buang masa untuk menulis question, because the time is limited, so you just need to write the answers. Okay, and make sure you highlight your answer so that easy for me to find your final answer. Okay. Okay, example 3.5. Okay, example 3.5. So let's do it. Okay, let's do it. So for an FM modulator with a peak frequency deviation 10 kilohertz. So now you are given the delta F 10 kilo, a modulating signal frequency FM 10 kilohertz also, carrier peak amplitude is 10 volt, and carrier frequency is 500k. So you see that you are given delta F, you are given FM, VC, and also the FC over here. Determine of what? Determine the actual minimum bandwidth from the Bessel function table. So you see that the word here, actual minimum or actual bandwidth, which is referring to the Bessel bandwidth. Okay, so in order to find the Bessel bandwidth, remember bandwidth by Bessel is equal to 2 times n times modulating signal frequency. So how much is n? So n, in order to find the value of n, we need to determine how much the value of beta. So beta F is equal to delta F divide over modulating frequency, which is 10 kilo over 10 kilo also. So this is equal to 1. Okay, equal to 1. Okay, so therefore we can find the n based on the table n equal to 3. Okay, according to Bessel table, for beta F equal to 1, n will be equal to 3. Okay, so we can put inside the equation 2 times 3 times Fm is 10k. So this is equal to 60 kilohertz, 60 kilohertz. Okay, 60 kilohertz. And then what? Find the approximate minimum bandwidth using Carson. So now want to find the bandwidth by Carson, which is equal to 2 times delta F plus Fm. So this is equal to 2 times delta F is 10 kilo plus Fm is 10 kilo. So 20 times 2, you're gonna get 40 kilohertz. Okay, 40 kilohertz. And then what? Plot the output frequency spectrum for the Bessel approximation. Okay, so plot the frequency spectrum. So this is similar with the previous example. Okay, so but now the question does not mention whether this is a relative amplitude spectrum, or power spectrum. So therefore it's up to you. Okay, so terpulang lah. Let's do based on the previous example. Mari kita buat seperti yang lepas. Okay, let's do like the previous. Okay, so we can draw a table. Okay, we can draw a table like this. Sorry. Okay, so this is for Jn. So Jn, remember Jn for beta equal to 1, so you get here J0 equal to 0.77. Wait. So this is amplitude. Lower sideband, for example, we make it in terms of kilohertz, and then the upper sideband in terms of kilohertz, for example. So J1 so J2 and J3 equal to 0.02. Okay, so the amplitude J1 is J0 is equal to, sorry, V0 V0 is equal to 0.77 multiplied with VC. VC is equal to 10 volt. Okay, so you're gonna get here 7.7. Okay, there's no upper or lower because this is a center frequency at FC, which is 500K, and then for V1 is equal to 0.44 multiplied with 10, so you're gonna get 4.4 volt. Okay, 4.4 volt. And for the lower sideband, so this is located at FC minus FM, which is 500K minus 10K, so you're gonna get here 490 kilohertz. And for the upper sideband FC plus FM, this is 500K plus 10K. Okay, plus 10K, so you're gonna get 510. Sorry, 510. Yeah, 510. Okay, and then for the second sideband, which is V2, so we get 0.11 multiplied with 10, so this is 1.1 volt. This is located at FC minus 2 FM, so this is 500 minus 20, so So we get here 480 kilohertz. And for the upper sideband FC plus 2FM, this is 500K plus 20K, so we get 520. And for the third sideband, okay, for the third sideband is V3 equal to 0. 0.02 multiplied with 10, so equal to 0.2. And this is located at FC minus 3 FM, which is equal to 500 minus 30, so we get 470 kilohertz. And for the upper sideband FC plus 3 FM, so this is 500 plus 30 kilohertz, so this is 530 kilohertz. Okay, so again, if you want to draw wait. Okay, so if you want to draw a relative amplitude, it means this is Jn. Okay, so this is similar with the previous. So for example, here is the center 500. This is 501, 510. This is 520. This is 530. Okay, and this is the first sideband at 490. Okay, 490. Second sideband around 480 kilohertz, and the third sideband is located at 470 kilohertz. Okay, so if this is a Jn, so you can just put the J parameter 0. What happened? .77. This is 0.44, 0.11, 0.11, 0.02, 0.02. Okay, so this is if Jn versus frequency. If you want to draw amplitude spectrum, that means this is Vn versus f. Okay, so you just need to put the value of V, which is 7.7, 4.4, 4.4, 1.1, 1.1, 0.2, 0.2. Okay, okay. Okay, so if you if it is a power spectrum, then you need to put the power. Okay, put the power. So the reason I make a table, so that easy for me to know the amplitude and also to know the frequency location, so that easy for me to draw the spectrum. Okay, so any question you want to ask, okay, boleh tanya. If you want to ask question, please ask. I can further explain. If not, we can try the next example. Okay, kalau ada soalan boleh tanya. Okay, can I get your response? Are you still there, students?
Yes, doctor.
Okay. So my
Yes,
my
doctor.
my voice is clear or not?
Yes, doctor, it's clear.
Okay, thank you for the response. Okay, so if there's no question, I will move to the next slide. Okay, if there's no question, I will move to the next slide about deviation ratio. Okay, deviation ratio. So deviation ratio is uh, the worst case modulation index. Okay, so the first statement here say that minimum siapa tu? Please mute your mic. Please mute your microphone. Okay, it said that minimum bandwidth is greatest when the maximum frequency deviation is obtained with the maximum modulating signal frequency. So the deviation ratio is actually the worst case modulation index, or the widest, or the biggest value of the modulation index, which produce the widest frequency, widest bandwidth. Okay, so this deviation ratio is also known as the worst case modulation index and is equal to the maximum peak frequency deviation divided by the maximum modulating signal frequency. So this worst case modulation index produce the widest output bandwidth. Okay, and mathematically we can define the deviation ratio as delta F max divided with Fm max. Okay, so this is actually beta F max. Okay, this is actually beta F max, which is known as deviation ratio. Okay, so let's do the example. Okay, so determine the deviation ratio. Okay, determine the deviation ratio and bandwidth for the worst case or widest bandwidth of modulation index for an FM broadcast band transmitter with a maximum frequency deviation. This is delta F max, delta F max, and a maximum modulating signal frequency of 15K. So this is FM max. Okay, so you can cancel the question below, cancel this one. Okay, so the question, the above question asks about dr. So dr is equal to delta F max divide with delta, sorry, divide with Fm max, divide with Fm max. So this is 75K divide with 15 kilohertz. So this is equal to 5. Okay, equal to 5. Simple. Okay, simple, straightforward. The next topic is about power in angle modulated signal. So this is a very important topic. Okay, very important topic. Of course, it's gonna come out in the exam. Of course, dia akan keluar dalam exam. Okay. So power in angle modulated signal. So if it is an angle modulated, that means it is for both FM and PM. Okay. So the way we want to calculate the total power, it is equal to 1 over 2 Vc square multiplied with summation of Jn square from minus infinity to infinity. Okay. So you might wonder where is the R value. Okay. So in this equation, it is assumed that R is equal to 1. Okay, there is actually r over here, divide with to r actually. Okay, r is assumed as 1 in this slide. Actually there's a r. So the power equation is still the same from previous, now, and in the future we still use the same power equation. Okay, the concept is still the same. Okay, so in this slide it is assumed that the resistance is equal to unity, which is equal to 1. Okay, so you see that this part, the Jn square part, this one. Okay, so according to Bessel properties, according to Bessel function properties, summation of Jn square from minus infinity to infinity will produce equal to 1. Okay, this is based on the Bessel. This is the Bessel properties. It said that summation of Jn square from minus infinity to infinity would be equal to 1. Okay, so therefore the total power would be equal to Vc square over 2, or here is actually 2R actually. Okay, so this is actually the carrier power. Okay, so that means the total power is equal to the carrier power. Okay, so theoretically the total power for angle modulated signal is equal to the carrier power. Okay, so we're going to see about this later. Okay, we're going to see about this in the example. Okay, okay, and remember about the carrier power. Carrier power is equal to Vc square over 2R. Okay, Vc square over 2R. And remember, when we want to calculate the total power, we are actually adding all the power for all components. Okay, carrier component, first sideband, second sideband, third sideband, and so on. Okay, so if you want to use the long equation, okay, the long equation like this, P total is equal to P0, the carrier component, plus 2 times the sideband, because we have upper and lower, so that's why we multiplied with 2. Okay, kita darab 2 kerana ada upper and lower sideband. Okay, so 2 times P1 plus P2. P1 is the power of the first sideband, P2 power of the second sideband, P3 is the power of third sideband, until power of the n sideband. Okay, and here P0 is equal to V0 square over 2R. P1 is V1 square over 2R, V2 square over 2R, until Vn square over 2R. So what is Vn? So Vn is equal to Jn multiplied with Vc. Okay, Jn multiplied with Vc. So that means this is J0 multiplied with Vc, J1 square multiplied with Vc square. This is J2 multiplied with Vc. This is J3 multiplied Vc square. This is Jn multiplied with Vc square. Okay, and if you see from here, there's a carrier component actually. If you see from here, each of these component, okay, each of these component consists of Vc square over 2R. This part, Vc square over 2R. Okay, Vc square over 2R. So Vc square over 2R is actually Pc. So if you want to rewrite the equation, it becomes J0 square Pc. Pc is Vc square over 2R, plus 2 times J1 square Pc plus J2 square Pc plus J3 square Pc until Jn square Pc. Okay, And theoretically these all will be equal to PC. Okay, theoretically it will be equal to PC, which is VC square over 2R. Okay, so if you want to ask me in the exam, which one should I use? Should I use the long equation, or should I just write equal to PC? Okay, so the answer is, okay, you can use either of it. Either you want to use long equation, or you want to write total power equal to PC. Both are correct. Okay, both are correct. Okay, so in the exam you can choose. If you want to write a total power using a long equation, correct. If you want to use total power equal to PC, also correct. Okay, so I will show you later that the total power is actually equal to PC. Okay, and if you see from the last statement here, okay, the last statement, it is said that the total power in the carrier and the sideband components are approximately equal to unmodulated carrier power. So you will see later that when you try the difference between a long equation and PC, okay, there might be a slightly different in terms of decimal point. Okay, in your calculation later, you're gonna see that there will be very small difference. Why? Because the Bessel table in your lecture notes, in the notes, has neglect the value less than 0.01. So that's why later you're gonna see that there will be slightly different in terms of values, very small difference. Okay, but theoretically total power is equal to carrier power. Okay, secara teorinya total power is equal to carrier power. Okay, so we're gonna see the next example so that you can have a clear picture about this situation. Okay, let's do example 3.7. Okay, example 3.7. An FM signal is given as VFMT equal to 12 cos 6 pi times 10 power of t plus 5 sine 2 pi multiplied with 1250t. So if I'm given this kind of question, what I should do? Okay, my suggestion, when you are given this kind of question, straight away identify the given parameters. Terus dapatkan parameter yang diberikan. Okay, from the given equation, I will know that this is actually equal to VC, 12 volt, and this is actually equal to FC. So how much is FC? So I need to divide with 2 pi, so I get FC. Okay, which is, if I divide with 2 pi, it's gonna be 3 megahertz. Okay, 3 megahertz. And then over here 5, this is actually beta f. Okay, and what about this? This is modulating signal frequency, which is FM. Now, so I already know many parameters. Okay, so determine the first question, frequency of the carrier. So we already know. So frequency of the carrier is actually equal to 6 pi times 10 power of 6 divided with 2 pi. So we get here is 3 times 10 power of 6 hertz Okay. And then what? Frequency of the modulating signal. Frequency of the modulating signal. So that means this is okay, frequency of the modulating signal is equal to 1250 hertz given in the question. Okay, 1250 hertz. And then what? Modulating signal frequency beta f, modulation index beta f is equal to 5, also given from the question. Okay, and then what? Frequency deviation delta f. So delta f is equal to beta f multiplied with modulating signal frequency, which is 5 multiplied with 1250. So you're gonna get this, how much is this? So 5 multiplied 1250, so you get 6250. Okay, 6250 kilohertz. Sorry, 6250 hertz. Remember to write the unit. Remember to write the unit. Okay. And then what? Power dissipated in 10 ohm resistor. So now you are given R. Find the total power. Okay, power dissipated. So this resistance. So where is this actually? Okay. So if you draw the transmitter, okay, this is transmitter, and we are actually supplied the current towards the antenna, so that antenna will radiate the given input. Okay, so these are normally it is referring to the resistance of the antenna. Okay, normally. Okay, biasanya normally in the exam we mentioned that the antenna resistance is 10 ohm, something like that. Okay, or 50 ohm, it depends. Okay, so total power is equal to so if you see from the Bessel table, let's look at the Bessel table. If 5, okay, if beta is equal to 5, we're gonna get up to how much? Okay, up to 8. Up to 8 sideband. Okay, 8 pairs of sideband. Okay, either you want to use a long equation or you want to use the short equation. Okay, so if you want to use the long equation, that means this is J0 PC plus 2 times J1 square PC plus J2 square PC plus until J8 square PC. Okay, which this will finally give the value of PC, which is VC square over 2R. Okay, so this is actually equal to VC is given 12 square divide with 2R. R is given 2 times 10. So this is equal to 7.2 watt. Okay. 7.2 watt. So you can try use your calculator. You should get 7.2 watt. Okay. So any question you can ask, otherwise we can look into the next example, this example. Okay, so if you have question about this, please ask now. If not, I will move to this example 3.8. Okay, so this example 3.8 actually wants to show you the difference, okay, of using a long equation and using a short equation for the total power. Okay, it wants to show you the slightly difference. Okay, so we're gonna try about this. We're gonna try this. Okay, so determine the unmodulated carrier power for the FM modulator given that beta equal to 1, VC 10 volt, R equal to 50 ohm. Determine the total power in angle modulated wave. So if we use the short equation, P total equal to PC, so this is actually equal to VC square over 2R, which is equal to 10 square divide with 2 times 50. So you're gonna get this equal to 100 and 100, so 1 watt. Okay, 1 watt. But if I want to use a long equation, okay, if I want to use a long equations, so for beta equal to 1, n equal to 3, and we already know the j. I already remember the j, so you can look into the table. So P total is equal to J0 square PC plus 2 times J1 square PC plus J2 square PC plus J3 square PC. Okay, up to 3. Okay, so that means here is 0.77 times 1, okay, plus 2 times 0.44 square times 1 plus 0.11 square times 1 plus 0.02 square times 1. Okay, so this is square. Okay, 0.77 square. So if you try use your calculator, 0.77 square, you get 5929 0.5929 plus 2 times so 0.44 square plus 0.11 square plus 0.02 square. So I got this 0.2061. 0.2061. Okay, remember PC we already get from here, PC. Okay, so I just want to compare. Okay, I just want to compare. And if you try this, multiplied with 2 plus 0.5929, you're gonna get 1.0051. Okay, so the difference is only a few decimal point only. If you get 2 point something, something wrong, your answer is wrong. Okay, it must be within decimal points difference. Okay, so why is this different? Because theoretically you're supposed to get 1. but now you get 1.0051. Okay, so it is not exactly the same because the Bessel table in your lecture notes, in the notes, has omit the values of sideband less than 0.01. So that's why you get slightly different. Okay, so it is stated here, the table has rounded up the value of sideband that is less than 0.01. So the table does not, the table in your notes does not consider the sideband values less than 0.01. So that's why the total power that you get, 1.0051, is slightly different from 1 watt. Okay, so if you ask me which one should I use in the exam, okay, which one should I use in the exam? So you can use either of it, no problem. Okay, you can use this short equation, no problem. If you want to use this, no problem. Tidak ada masalah. Okay, both are correct. Okay, so now is okay. So if you have a question, you can ask. Otherwise, I will maybe I will show some of this. Since we have another 15 minutes, okay. So I will use all the time. So don't worry about that. So including me, I also feel tired now, but we need to use the time. So maybe I will answer some of it. Maybe I will answer some of it since we have a few minutes. Okay. So let's use all the time. Okay. So example 3.9 is a good example, which is similar with the final exam pattern. Okay, so the final exam pattern, something like this, where we ask you starting from the equations until the few parameters, and then the last one will be the power. Okay, so this is a good example for the final exam. Okay, so the pattern is something like this. Okay, patternnya seperti ini. Okay, if you see from here, FM signal, the FM signal is given as 1000 cos 2 pi times 10 power of 7 plus 0.5 sine 2 pi 10 power of 4 is measured in a 50 ohm of antenna resistance. Determine the following. Okay, determine the following. So you are given VC, okay, 1000 volt. You are given FC, which is 10 mega. Okay, this is actually 1 times 10 power of 7, which is 10 mega actually. And then you are given beta F, which is 0.5, and then FM is 10 kilohertz. Okay, so what? So the question asks, find the unmodulated carrier power. So the question asks you to find PC. So PC is equal to VC square divided with 2R. So this is 1000 square divided with 2 times 50. So how much is this? 1000 square divided with 100. So you get 10,000. Okay, 10,000. Modulation index, so we already know the modulation index is from the question, which is 0.5. Okay, which is 0.5. Peak frequency deviation, delta F. So delta F is equal to beta F multiplied with modulating signal frequency FM. So this is actually equal to 0.5 multiplied with 1 4. So how much is this? So this is 5. So 10 kilo divided with 2, so we get 5 kilo, 5 kilohertz. Okay. Find the modulation sensitivity parameter, KF. Okay, find the KF if you are given if 200 millivolt is required to achieve part C. What is this? Okay, in order to achieve so the part C is this one. Part C is number 3. So we need 200 millivolt. So this is what? Actually, this is referring to the modulating signal amplitude. Okay, we need to find KF given VM. Okay, given VM. Okay, so remember that beta F is equal to KF VM over FM. Okay, so if you want to find KF, so KF is equal to beta F multiplied with FM divided with VM. So this is equal to, so we already know how much is we already know beta F. We already know beta F. Okay, which is beta F multiplied with FM. We already know from part C, from part 3. Okay, which is 0.5 multiplied with 10 kilo. So we get here is 5 kilohertz. So 5 kilohertz divide with 200 millivolt. So how much is this? So 5 kilohertz, 5k divide with 200 milli. So we get 25,000. So 25,000 kilohertz per volt. 25 kilohertz per volt. Okay. And then what? Draw the amplitude spectrum. So you need to refer to the table. Okay. Refer to the table, then you need to find the bandwidth. Sorry, refer to the table, then you can get the values. Because this is beta F 0.5. If you see beta F 0.5, 0.5, you get up to 2 pairs of sideband. Okay, so 0.94, 0.24 and 0.03. So we have up to 2 pairs of sideband, 94, 24, 03. Okay, 94, 24, 0.03. Okay, 94. Okay, so this is the J, J0, J1, J2. So you need to find V1. V0 is equal to times 1000. So 940 volt. You multiply with 1000 for the VC. Okay, so V1 is equal to 240. Okay, 240 volt. Okay, and V2 is equal to 30 volt. Okay, so I multiplied with 1000 because VC is equal to 1000 volt. Okay, and then I can draw the spectrum. Okay, I can draw the spectrum. Okay, I can draw the spectrum. I have here up to 2 pairs of sideband. Here up to 2 pairs of sideband. Okay, so for example, this is in megahertz. Okay, F megahertz. This is voltage versus F. Okay, and here is a 940. This is 240. 240. This is 30. 30. And the frequency is the center frequency is 10 megahertz. 10 megahertz, and then the carrier is 10. So this is FC plus FM, 10 mega plus 10, so this is 10.01, 10.02. Okay, so this is 9.98, 9.97 mega. Okay, so FC plus FM, FC plus 2 FM, FC minus FM, FC minus 2 FM. Okay, so I draw this spectrum. Okay, and then the bandwidth 99%. So this one gonna take. So this one 6 until 7 I will explain next week. Okay, so panjang sikit ceritanya. So I need more time to explain 6 until 8. Question 6 until 8. So that's all for today. So see you again next week. So before next week, see you again on Friday. Okay, remember we have tests on Friday at night, 8 to 9:30 p.m. So make sure you take note. Okay, make sure you take note this schedule. Okay, please, I hope that nobody sleep at 8 o'clock at night. Okay, at that time, so because you need to answer the question. So the topic would be from chapter 1 until AM power calculation. Okay, there gonna be 3 questions. First question for chapter 1, second question for chapter 2, the third question is for chapter 3 until AM double sideband full carrier power calculation. And I suggest you to look into the multiple input frequency in chapter 3 about the power calculation for the multiple input. You will see from that. So I also would suggest you to practice answering the previous semester's test question. Okay, and most of the question that has been come out has been teach in the class. I already explained everything in the class actually. If you follow my lecture session, you know that I already explained all of it actually. So you have learned actually. Okay, you just need to refresh again what you have learned from the notes. You can learn from my lecture video, and you can try from the previous semester exam question. Okay, so yeah, so total marks would be 60. So 20 marks, 20 marks, and 20 marks. So 60 marks, 60 marks. In total, you're gonna come up as 20% of your coursework marks. Okay, so you still have time to study. So no problem. I believe you can score the test. No problem. Okay, and maybe later I will detail the topics that will come out in the test, so that you can more focus on that specific topic. Okay, so that's all for today. So you can open your QR code reader to take the attendance, and then you can go out to anywhere you like. Okay, so open your QR code reader and take the attendance. Okay. Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Dr. Be safe.
Okay, you too. Thank you.
Doktor, saya tak boleh nak scan lah, Doktor.
Tak boleh nak scan?
Thank you, Doktor.
Okay, welcome. Siapa yang tak boleh scan tadi?
Thank you, Doktor.
Okay,
Nurul
okay.
Amira, Doktor.
Nurul Amira. Nurul. Okay, done.
Thank you, Doktor.
Okay, welcome.
Doktor, sama tak? Muhammad Alif Aiman.
Muhammad.
Doctor, please can you check now?
Muhammad
Alif
Alif
Aiman.
Aiman.
Muhammad Syahim, Doktor.
Seorang-seorang tadi siapa tadi?
Doctor,
Yeah. What's your name?
Doctor, my name is Sundus.
Oh, Sundus. Okay, done.
Saya Doktor, nombor 10. Muhammad
Nombor
Alif Aiman.
10. Muhammad Alif Aiman. Okay, done. Siapa lagi?
Thank you, Doktor.
Okay, welcome. Who else?
Saya Doktor Syahim.
Syahim.
Muhammad Syahim.
Muhammad Syahim. Syahim. Okay, done.
Okay, Doktor, thank you.
Nombor 15, Doktor.
Thank you, Doktor.
Muhammad Amirul Amri Adam.
Amirul Amri. Okay, done.
Okay. Thank you, Doktor.
Okay, welcome. Who else? Siapa lagi?
Doctor. Doctor,
Well.
can you back example 3.7? I need to say one more.
Wait. Any more attendance? Where is Iza and Kumaran? Wait.
Okay, Doctor.
Kumaran baru masuk So Iza and Kumaran is there.
Bukan doktor. Tadi terkeluar doktor.
Oh, okay. So Iza is attended. Kumaran also. Okay. So done, Kumaran.
Okay, thank you doktor.
Okay, welcome. Who's Sundus? You ask question or what?
Yeah. Example 3.7. I need 3.7.
3.7. This one.
Yeah.
Okay.
Yeah. Okay, Doctor. I need to see the last solution answer. Oh, now I see. Thanks, Doctor.
Okay, done.
Okay, then thanks a lot, Doctor.
Okay, welcome.
Okay, bye.
Okay, bye.